Okay guys, today we're going to be solving this linear second order ODE, and I like to call it the Fibonacci differential equation because it has the same sort of form. Y double prime is equal to sum of y prime and y. I don't know. So first thing we're going to do, we're going to subtract y prime and y. Okay, and we're going to get the zero function on the right side. Now, notice, over here we have all these derivatives of y's. And then over here we have the zero function. So what does that mean? That means all these functional parts of the derivatives of y cancel out. So that means, the functional parts of y and its derivatives should be about the same. So what do we know that has something like that? Well, we can try and check what would happen if you use the exponential. Okay, so here's a general form of the exponential function. Let's go ahead and solve for y prime. We get mu r e to the rt plus c goes away, y double prime is equal to mu r squared e to the rt. Plugging this back into our differential, we get our differential equation. We get mu r squared e to the rt minus mu r e to the rt minus mu e to the rt. And then minus our c at the end, and we get the zero function, okay? Alright, so we have this. Notice, there is only one constant part in this entire equation, and that's the minus c. But on the right side, we have no constant part, it's just a zero function. So what does that mean? That means that the c is actually going to be 0. So that's gone. Okay, cool. Now, one thing I'm just going to impose temporary. Oh, one thing is we can have two cases. Okay, case 1. This is where mu is equal to 0. If mu is equal to 0, then we do indeed, we get that y is the zero function, and y prime is a zero function, and y double prime is a zero function. So that does indeed solve the differential equation, but it's very boring, and we don't have to do all that work to figure out 0 as a solution, right? So that's pretty boring. But let's go ahead and check out case 2, where mu is not 0. Well, we can factor out. Notice you have a mu e to the rt, mu e to the rt, mu e to the rt. We can factor that out and divide it. So we get mu e to the rt times r squared minus r minus 1. This is equal to the zero function. Because mu is not 0, we can divide out by this, and we know e to the rt is never 0. We get that r squared minus r minus 1 is equal to 0, and this is called the auxiliary equation. Now we solve it, and we get that r is equal to 1 plus or minus square root of 5 over 2, okay? You could just use a quadratic formula. This is actually a very famous constant. It's the golden ratio. It's also his little brother. So we have phi and phi bar, which is very nice. Now that we solved r, we can go ahead and put it into y. So we see that y of t is going to be mu e to the r. It's going to be phi t. And there's another value of r, so we can go ahead and add that in. So it's going to be mu e to the phi bar t. And also we have the zero function. So that's one way you can write the solution. But indeed, there's some other ways. So, first things first. This 0 at the end is completely redundant because mu, even though we said it earlier that it can't be 0, but for now we're going to say it can be 0 again, so there we go. Second of all, this differential equation is called linear. So, what we can do is set y of t to b. First things first, I'm going to rename this one here to be a, and e to the phi t. And then I'm going to rename this to be b, e to the 5 RT, okay? And then bam. We have our solution to our differential equation, our general solution right here. And indeed, when you plug this in, you'll see that it works.